So it's our pleasure to have a local host from Jagiellonian University, Nikolai Poplawski, who will talk about big bounce inflation from spin and torsion. Please.
Thank you very much. Thank you very much for inviting me for this great workshop. So I wish I were in Krakow in person, because 20 years ago I was a student for 1 year at Jagiellonian University. Now I'm in the United States, so greetings from here. So here my talk will be about how spin and torsion can solve some problems in cosmology. So here is this famous picture that can be found on different websites, and I made some little modification here. I think where my cursor shows, there is the Big Bang, but I replaced it with Big Bounce, because this is an alternative which can be produced by torsion. And immediately after Big Bang or Big Bounce, we think that there was a period of rapid exponential expansion of the universe known as inflation. And then 380,000 years after the Big Bang, the cosmic microwave background was produced. And then 1 billion years after, like, stars and galaxies were formed, and we have expansion of the universe. Now, of course, we don't know everything about the universe, because we have things like dark matter and recent accelerated expansion of the universe known as dark energy. So, but I want to concentrate today on the early universe, which means Big Bounce and inflation, as I mentioned in my talk. So, problems of general relativity. So cosmology, the science about the universe, is based on general relativity. General relativity, according to Einstein, describes gravity as a curvature of spacetime. Now, the problem with general relativity is that it admits the existence of singularities, which are points where curvature and density of matter are infinite. Secondly, we don't know yet consistent quantum theory of gravity, and many physicists believe that quantization of gravitational field may resolve the singularity problem. And there is another issue which is not maybe very famous among physicists studying general relativity, that according to general theory of relativity, we can build a theory of spinor fields in presence of curved spacetime, and we can construct the Dirac equation in curved spacetime. However, such Dirac equation will be not consistent with general relativity completely, because general relativity, the conservation laws in general relativity imply that orbital angular momentum of a free particle is conserved, but Dirac equation gives the conservation of total angular momentum, orbital plus spin. So there may be some exchange between orbital and spin angular momenta, which is observed in quantum mechanics, but this is not fully allowed in general relativity. So there must be some extension of general relativity to make it completely consistent with spin-orbit exchange allowed by Dirac equation. And the simplest extension of general relativity which allows spin-orbit exchange is the Einstein-Cartan theory. The Einstein-Cartan theory is almost 100 years old. Cartan invented torsion tensor in 1921 or 1922, several years before Schrödinger invented the wave function. So it is an old theory, but then it was a little shadowed by other theories which were rising. So now what is interesting about Einstein-Cartan theory is that not only it could resolve the problem of total angular momentum, but also it may resolve the singularity problem. And this is why I got interested into this theory about 15 years ago. Problems of Big Bang cosmology. So of course, Big Bang singularity, which is according to Friedman equations of the universe, if we assume that they're classical, the universe started from a very, very hot and dense state, which ideally, according to the equations, was a point. And so that's a problem because we have infinity. Now, of course, what caused the Big Bang, what existed before, so they could be physical or maybe even philosophical questions. Then we have inflation. Inflation is the great paradigm which solves the flatness and horizon problems and also gives the observed spectrum of cosmic microwave background perturbations. But we have questions what caused inflation, and usually physicists consider hypothetical scalar fields like inflaton or maybe other fields. Now there is also the problem how inflation ends, because we don't observe inflation right now. We don't have something called eternal inflation. So there are some issues, and of course they can be solved using complicated models, but here I kind of want to propose that it may be the Einstein-Cartan theory which could solve some of those problems. And I started investigating this about like 15 years ago, but 10 years ago there was the article showing how exponential inflation and big bangs can arise in Einstein-Cartan theory. So here just something about closed universe. So this is like the model which I personally favor, and there was a recent paper by Joseph Silk in Nature with two collaborators that there may be some evidence that universe may be closed, but if universe is closed, it will be analogous to the two-dimensional surface of three-dimensional sphere. So the universe, which is of course three-dimensional in space, as far as we know, can be mathematically considered as the three-dimensional surface of four-dimensional hypersphere. But this hypersphere is purely mathematical. And here in the picture, there is like this balloon, right? So this is the analog. Universe would be, in this analog universe would be, if the universe were two-dimensional, it would be two-dimensional sphere of two-dimensional surface of three-dimensional sphere. The radius of this balloon in this picture is the scale factor. We know that universe is expanding. And this is analog of closed universe. If universe was flat, then the two-dimensional analog of the universe would be just simple plane. And if it was open, then it would be a saddle. It's kind of difficult to imagine a saddle in more dimensions, but well, mathematically that would be equivalent. So here's Einstein-Cartan-Sciama-Kibble theory of gravity. So Einstein-Cartan gravity was explored in the 60s by Denis Sciama and Tom Kibble, and they made some discoveries about it. So basically, there is a torsion tensor. Torsion tensor is an additional variable. So in general relativity is based on the metric tensor. That's like the only dynamical variable, and Einstein equations can be solved for the metric tensor. In Einstein-Cartan theory, we have two fundamental tensors, metric and torsion. So torsion tensor is antisymmetric part of the affine connection. So in general relativity, affine connection is given by Christoffel symbols, which means affine connection is completely built from the metric tensor. However, if we allow this additional degree of freedom, if we allow affine connection not to be symmetric, that was an assumption. There was an assumption that affine connection is symmetric. If we allow affine connection to be not symmetric, which means to possess torsion tensor, then we have a richer structure. Now, Einstein-Cartan theory is as simple conceptually as general relativity, because the first of all, the covariant derivative of the metric tensor also vanishes. Now, in general relativity, if affine connection is symmetric, the covariant derivative of metric tensor equal to 0 gives us Christoffel symbols. Now, if we allow affine connection to have antisymmetric part, then this condition will gives us affine connection as sum of two terms. One will be purely metric part, which is Christoffel symbols, and there'll be another part, which is the linear combination of torsion tensor. And secondly, the Lagrangian density of gravitational field in Einstein-Cartan theory is also simple as it is in general relativity. It is basically R times some constant. It is proportional to the Ricci curvature. Now, in general relativity, Ricci curvature scalar is built from metric tensor and its first and second derivatives. But now, in Einstein-Cartan theory, there will be some also contributions from torsion. And there is a beautiful decomposition, actually, the curvature tensor, which is built from the affine connection, which has metric and torsion, can be decomposed into two parts. One part is purely metric, the Riemann tensor, and the second part will have torsion and its first derivatives. And this is actually beautiful because in the next slide, I will basically show why it is beautiful. So in Einstein-Cartan Shamakibel gravity, since we have metric tensor and torsion tensor as two fundamental fields, then to obtain the equations, we need to use the principle of least action and do the variation with respect to metric and with respect to torsion. So when we do the variation of total action of matter and gravity with respect to torsion, then we will get the Cartan field equations. So basically, there is the first white box here. It is a linear combination of torsion tensor. So S is torsion tensor. Then you can see also the metric tensor, and SI, it is basically the contraction of, if you take two indices in torsion tensor, the ones which are not antisymmetric, and contract them, then you will get something called torsion vector with one index. So SI is torsion vector. So we get a linear combination of torsion tensors is proportional to a spin density. Spin density can be defined as the functional derivative of matter Lagrangian density with respect to contortion tensor, and contortion tensor is another linear combination of torsion tensors. And actually, this works for Dirac fields. For Dirac fields, actually, this functional derivative gives exactly what we want, the spin density for fermions. So basically, Cartan field equations are they are algebraic equations. You can see that torsion tensor S on the left-hand side is proportional to little s on the right-hand side to the spin density, which means in vacuum, when there is no spin density, then left-hand side will be also 0. In vacuum, torsion is 0. In vacuum, torsion is 0, and without torsion, Einstein-Cartan gravity reduces to general relativity, which means in vacuum, Einstein-Cartan theory is fully equivalent to general relativity. And since most of the tests of general relativity are vacuum tests, then all tests of general relativity are also tests on Einstein-Cartan theory. Einstein-Cartan theory passes all the tests as general relativity does. Now, if we don't have vacuum, then actually I'm going to get back to this point in a moment, because just on the bottom of the slide, when we make the variation of the total action for matter and gravity with respect to metric tensor, then we will get the Einstein equations. The curvature is proportional to energy and momentum, but we can also make the decomposition. So when we have Einstein equations, curvature proportional to energy momentum tensor, when you decompose curvature into purely metric part and the torsion part, then you can take the torsion part and move it to the other side of the equations. So the torsion part of curvature will be on the same side as energy momentum, and then we can use the Cartan equations to replace torsion tensor with spin density, because those are proportional to each other. So basically, all the torsion part can be moved to the side of Einstein equations where we have energy and momentum. So basically, as a result, we will get this equation which is on the bottom. Then Einstein tensor, GIK is equal to Einstein constant times energy momentum tensor. So this is general relativistic part, plus this long expression, which basically has the torsion part of curvature rewritten in terms of spin density. So basically, torsion contribution is basically equivalent as if we used general relativity from the beginning, but made some modifications to energy momentum tensor. So basically, Einstein-Cartan theory is equivalent to general relativity with energy momentum tensor modified by some corrections coming from spin density. And those corrections are quadratic in spin density. And also they include gravitational constant squared. So those corrections are very small. And those corrections are very small. And in order to for those corrections coming from spin density to be on the same order of magnitude as energy momentum tensor, which is used in general relativity, then the density of matter has to be very high. So basically, numerical estimations show that Einstein-Cartan theory will introduce some significant significant corrections to general relativity when density of matter is very, very high, approximately 10 to the 45 kilograms per meter cube and higher. And those densities, density of neutron star is like 10 to the power 17. So those densities are so high that basically torsion is irrelevant in neutron stars. It is irrelevant in solar system. The torsion tensor is really relevant only in two scenarios: in black holes, where densities can go even higher, or at the very early universe. And those regimes are the regimes that we need some help, because we may have singularities there, right? So torsion does not do anything to general relativity effectively at the densities and scales which are fine. Torsion may solve the singularity problem, which appears like when the densities go too high. So, okay, so this was done in the 1960s, like this decomposition, and I think there's like in 1974 there was published paper by Friedrich Hell and collaborators, which is like a review of current knowledge, and it is like a standard paper for scientists researching torsion. So, universe with speed fluid. So, Dirac particles can be averaged macroscopically as a spin fluid. So basically, spin tensor can be shown that for point particle approximation of matter, spin density here, the first equation on the left, can be actually decomposed into some tensor times for velocity, and there's some extra conditions. And basically, with this approximation, if we are using ideal fluid approximation, so basically in general relativity you have energy, density, and pressure of the fluid. Same thing will happen in Einstein-Cartan gravity, except that energy and pressure will be corrected by those corrections coming from spin density, and those corrections are here. Those are negative corrections. S square is negative. That's the average value of the square of spin tensor, because corrections coming from spin density to energy momentum tensor were quadratic. So we have to average the quadratic value, which means spin orientation is not super important, because we are averaging average spin. So even when orientation of spins in matter is random, the average square will not be zero. So there will be corrections to energy momentum tensor, and those corrections are negative. Those corrections are negative, which means when now, and they are also quadratic in spin densities. So at high densities, square of spin density will be increasing. Let's say if we extrapolate expansion of the universe backwards, when a scale factor decreases, then spin density will be growing faster than energy density and pressure. So those negative terms will be growing faster, and eventually effective energy density and pressure may become negative. So, and this is actually...
We have a question from Jakub Bilski.
Yes.
Yes, hello. So I have a quick question. So how much different that will be if we consider fermionic currents instead of coupling fermions, if we consider coupling fermionic currents, which are bosons, right? If we consider coupling them to the Einstein-Hilbert action. So how much different will be that when we compare it to your result in cosmology?
Oh, so here, in Einstein-Cartan theory, like we assume that like only fermions are that fermions are coupling to torsion. Fermions couple to torsion because in Dirac equation we have a covariant derivative, and covariant derivative will be now depending on torsion. So basically, the Dirac equation will become cubic in spinor fields. So fermions couple to torsion because the torsion exists in covariant derivative of the Dirac particle. Now for bosons, we know that photons don't couple to torsion because the gauge invariance would be violated, and the massive bosons like W and Z, I honestly don't know how they couple. I think there may be some papers on that, but I'm not sure. So there may be some. The other couplings could probably introduce some difference, but I'm not sure yet. But this is actually a nice idea a nice area to explore. Okay, may I continue?
Yeah, please.
Yeah. Okay. So those negative corrections to energy and pressure, they allow to violate a strong condition, strong energy condition in Raishal-Duri-Landau equation. So the Penrose-Hawking theorem will lose one of the conditions. So basically that's why singularity may be avoided because of those negative corrections. Now, if we assume that universe is closed, homogeneous, and isotropic, now actually, if it's not closed, if it's open or flat, then the +1 here and here will be either 0 or -1. But so this actually is also for open and flat. So if we assume that universe is homogeneous and isotropic, then we have Friedmann, Lemaitre, Robertson, Walker metric, and Einstein-Cartan equations become Friedmann equations for scale factors. So those equations in the white box here are Friedmann equations, but energy density and pressure are modified by these negative corrections from spin density, and S square in spin fluid approximation will be proportional to square of fermion number density. So if you know fermion number density, you know S square, and those are the Friedmann equations. And of course, like research done by Friedrich Hell, but also Polish professors in the 70s, Trautmann, Kopczyński, Kuchowicz, and several others, they were exploring. It was a very active area actually in Poland at the time, and how torsion basically through those negative corrections can induce repulsive gravity, so effectively. So then when we have relativistic matter, which is valid in early universe, then we can rewrite Friedmann equations in terms of temperature, right? So energy density is 3 times pressure. That's proportional to the 4th power of temperature. Number density is proportional to the cube of the 3rd power of temperature. We can substitute those. So basically, when you take n is here, you plug into S now goes into Friedmann equations, and then you can rewrite Friedmann equations in terms of scale factor and temperature only. And those constants H star and H and F, and those are constants which come from statistical physics. They depend on how many degrees of freedom, how many particle species existed in the early universe. So in my calculations in the published articles, I just assume that the only particles which existed in the early universe are the particles which we observe right now, which means the particles of the standard model, but who knows, there may be more, so those little values of H might be bigger, but it would not change really the order of magnitude. So we have those two equations, and then we can introduce non-dimensional variables. So X is temperature divided by critical temperature, and critical temperature is the combination of Planck constant, speed of light, gravitational constant, and those H constants, which are like coming from statistical physics. We can also define critical scale factor and critical and also some non-dimensional time. So basically we can, it is simpler to do it in terms of non-dimensional quantities. So X is basically this non-dimensional temperature and Y is non-dimensional scale factor. And we can get those nice two differential equations. And this was work I was doing 2 years ago with my student Gabe Unger here. So published in APJ, and those are two equations. And just to specify that the critical temperature is basically on the order of magnitude of Planck temperature, and critical radius is on the order of magnitude of Planck length. So actually here I kind of quietly assume that we can use classical equations. Who knows, the space-time may be quantized, but maybe not at this scale. So I quietly assume that this is classical. So we have this system of two differential, one equation, system of two equations, and now because what is interesting is that even in presence of torsion, we get the same dependence as without torsion, that xy equal to constant, basically temperature of the universe times the scale factor. This product is constant. So this is for relativistic matter, but even in the presence of torsion, in spin fluid approximation, it survives. Now, in other models with torsion, not in the spin fluid approximation, it will be the second equation on the bottom will be a little different. So there are some, even within Einstein-Cartan gravity, we may have different arguments for different models, but here I'm using spin fluid. So basically here's the equation, and this equation for closed universe, you can find turning points. Turning point is defined where the time derivative of the scale factor, which is y, that is equal to 0. And you can look for turning points. And it is a very nice, interesting observation that there are two turning points if the constant c, which is related to basically the product of the constant product of scale factor and temperature in the early universe. If this constant is bigger than some threshold, which is here 8/9 square root, then you have two turning points, which means universe have big bounce and big crunch. However, if this constant is 8/9 square root, then you have only one turning point, universe is stationary. And if the constant c, so basically if the product of scale factor and temperature of the closed universe are below some threshold, you cannot have such universe, which means there is a condition. It was a very, very interesting result that in order to create closed universe, the product of scale factor and temperature, and scale factor is can be calculated in terms of curvature of the space-time locally at the point where you want to create the universe, then product of scale factor and temperature must be bigger than some threshold. So now for flat and open universes, we also have avoidance of singularity, but there is no constraint on that product of temperature and scale factor. And of course here we have no cosmological singularity, because if you look at this equation, to make singularity, y would have to be 0, right? But y cannot become 0, because when y when the scale factor y decreases, then here, this second term in the first equation on the left is negative. It will be dominant term. So basically, at sufficiently small value of scale factor, the right-hand side of this equation could become 0, but you cannot have it because left-hand side is positive. And even if universe was flat or open, if +1 was replaced by 0 or -1, still right-hand side cannot be 0. It cannot be negative, which means y cannot become 0. So we have avoidance of cosmological singularity here. So we are creating the non-singular bounce. And here are some little graphs like how for different values of this integration constant c, which again, it is the product of temperature and scale factor in non-dimensional units, we have this bounce, right? So here's the idea. The idea is that if closed universe, so open and flat universe, there is no constraint on the value of constant c. But for closed universe, the constant c, which is non-dimensional product of scale factor and temperature, has to be bigger than square root of 8/9, which means the idea is that a universe could form basically at some region in space-time somewhere where this threshold is achieved. If the scale factor times temperature is bigger than the threshold, then universe could form. So, and c is on the order of 1, right? However, then right after the formation of the universe, right when you have like quantum effects at strong gravitational fields, they produce intense matter production, and constant c may be increased to the current value. Right now, the current value in non-dimensional units of c is 10 to the power of 30. So, and actually inflation can make this increase. So now I kind of wanted to go, so basically, so closed universe by itself, basically, if there was no matter production, then closed universe would be oscillatory. You would have big bounce and a big crunch, and you kind of and you oscillate. However, every bounce would be non-singular. So you have cyclic universe. So without matter production, there would be cyclic universe, but it would be non-singular universe. Each bounce would be non-singular. However, if you have matter production, then each cycle would last longer, and each cycle could lead to bigger scale factor at every crunch. So there'll be like a universe which is like and growing. So each cycle would have bigger maximum value of the scale factor. However, thanks to dark energy, at some point, universe reaches the size where energy dominates, and universe can escape this cycle of those bounces and can escape to infinity. So basically here on this graph, like, so here's this graph coming from, those are graphs for different values of cosmological constant. So if you consider closed universe with a cosmological constant, then depending on the value of the cosmological constant, you may have different scenarios, and they were like Bondi did them like 50 years ago. But basically, let's say here on the bottom, I have like some little cycle which ends with a non-singular, well, you cannot see that, but yeah, non-singular bounce. Then the next bounce would be bigger because here near the bounce we produce a lot of matter. So new bounce could have start the bigger cycle, but then if cosmological constant is not big enough, then actually it would result with coming to the crunch. However, if cosmological constant is big enough, then actually the universe could actually reach the size where cosmological constant is now dominant, and actually you can follow this curve here. You escape from the bounce, from the cycles, and universe expands to infinity, which means.
Excuse me, we have a question from Daniel.
Yes.
Nemeth.
Hi. I would like to ask, what's the probability of reaching this lambda equal lambda critical? Because that's also a possibility, because then there will be no bounce, no evolution.
Oh, so of course, Depends on the so I assume here that at every bounce there is a matter production of matter, and like papers in the 60s and 70s by Zeldovich, Starobinsky, Parker, they're like models of production of different parts of different kinds of particles. So basically, when universe would be in this series of bounces, every cycle will lead to bigger value of the maximum scale factor. So basically, eventually, the universe for any value. So actually, I should be more specific. So basically, for any value of cosmological constant, universe would reach the size at which cosmological constant becomes dominant, because the bigger universe, then the more energy of universe comes from cosmological constant. So basically, depending on the value of cosmological constant, if cosmological constant was smaller, universe would need more bounces to reach the size where it become important. Yeah. So the number of bounces depends on the value
can it get trapped
of cosmological constant, and also depends on the value of the production of matter. So basically here, now here's the last part, matter production. So here's the proposal that inflation is caused by matter production. Because here is what I did like 4 years ago. So I assumed that this Parker, Starobinsky, Zeldovich particle production, and for dimensional reasons, the particle production, which is basically the time derivative of the concentration of particles produced, dN over dt is proportional to the 4th power of Hubble parameter, and the constant of proportionality is beta, which is some parameter. This is the only free parameter I don't know. But we don't have complete theory of particle production, but some papers differ by those values of beta. It's like 1 over 120 pi, or maybe 1 over 360 pi. So the different papers have different values, but they are approximately about 1 over 1000, all of them. So here, when you put the particle production, then the Friedmann equation. So one of the Friedmann equations was here, right? This one. So this is the Friedmann equation, the second Friedmann equation, which is without particle production. With particle production, you have this extra term. And now when you look at this equation, you realize that, first of all, this term in this equation, the term which has beta, the whole term cannot be bigger than 1, because if this term will become bigger than 1, then the term on the left-hand side will become negative, and then basically growing scale factor will grow the temperature, so we'll have eternal inflation. To avoid eternal inflation, this term with beta has to be less than 1, which means the maximum value, the maximum of this function, which has a dot, a, and t, has to be such that this term is little less than 1. So this introduced the upper limit on this production parameter, which is 1 over 929, which is kind of similar to those values of Parker, Starobinsky, Zeldovich. So maybe it may look like that this value maybe like fine-tuned, but actually it is close to the models which independently gave the same order of magnitude. So if beta is very close, but a little smaller than this critical value, then the maximum of this function here in the beta term will be very close to 1, which means right-hand side will be close to 0. So, and this temperature, that temperature will be constant. But if temperature is constant, then actually, and a dot. But basically, from this equation, we can find that this will actually mimic the exponential expansion. Temperature is constant. Hubble now this second term in the middle is almost 1, so A dot over A is almost constant. So Hubble parameter is constant, temperature is constant. This gives basically constant energy density, and this gives exponential expansion. So there is a small period, a very short period of exponential expansion. Eventually, this term, the term 1 minus the term, the beta term will get less than 1, and inflation will end, and then eventually torsion tensor becomes weak, and the dynamics go basically from torsion domination go to radiation domination. So basically here, what I'm arguing is that torsion, spin and torsion together can actually produce inflation. And just to finish, there are some, depending on the value of beta, here's the ratio of beta to the critical beta, we may have different number of bounces. So for example, if particle production is very, very close to the critical production, cannot be bigger because you would have eternal inflation, then you have one bounce. And basically one bounce is good enough. After this bounce, so much particle production is made, then the universe is already ready to go and reach the size where cosmological constant dominates and can expand to infinity. However, if the value of beta is smaller, you'll have more bounces. And this table shows basically some number of bounces. Here is some diagram showing basically how initial value of scale factor is not very important. Actually, those results are not too sensitive to initial value of the scale factor, because here basically we have number of e-faults. Number of e-faults is very sensitive to the how close this beta is to the critical value of production, but not very much to initial scale factor. And here is dynamics for when beta is almost equal to critical beta. And here is, for example, some graph showing how you have inflationary period. That's a logarithmic graph. So you have like how scale factor grows exponentially, which looks like a line on logarithmic graph, and then eventually torsion becomes weak, and then it becomes a regular relativistic radiation dominated expansion. So basically we have finite period of inflation, and here the last thing would be that you can always find a scalar field. So I did not use any scalar fields. Big bounce and inflation come from torsion and matter production. But when you have dynamics of scale factor, you can go backwards, and there was a paper by Ellis and Madsen who reconstructed what, if you know the time dynamics of scale factor, you can always find out what is the potential, what is the scalar field which would give us the same dynamics. So basically, with my colleague, Dr. Desai, he reconstructed. So we found the time dynamics right after the last bounce, and last bounce is the Big Bang, basically, because if you have several bounces, last bounce is the Big Bang of the universe. We analyzed the dynamics after the last bounce, and then we found what would be scalar field potential, which would give us the same dynamics. And this potential looks like this. It's a plateau-shaped potential, and plateau-shaped potential is favored by Planck 2013. So this is the inflation model. Favored by Planck, and basically spin and torsion and particle production can create dynamics which is equivalent to scalar field. So we don't have scalar fields, but we create a plateau dynamics which is equivalent to plateau scalar fields. And also here just shows some graphs showing that when beta, there are some regions of particle production which gives us consistency with the observed value of scalar spectral index and tensor to scalar ratio. Again, initial scale factor is not super important. You have like a whole bunch of like 10 to the minus 26, 10 to the minus 16, even like if you go a little smaller values of initial scale factor. Basically the particle production parameter is a very important parameter, and that's the only parameter which we don't know. And kind of want to finish that the closed universe the idea, something about baby universes, Novikov, Patria, Hawking, Smolin, myself, and several other people came up with the idea that every black hole creates a new universe on the other side of event horizon, and our universe could have originated in the black hole existing in some bigger universe. Now, why is it so? Because when matter collapses, just before matter would like to collapse to a singularity in a black hole, then torsion becomes strong, and torsion violates formation of singularity, so the matter has to stop and has to bounce back. But the matter cannot go back through the original event horizon, so it has to create new space. So basically, it creates a baby universe. So basically, torsion may be a mechanism which allows for black holes to avoid singularities and create baby universes. And in this case, paradox information could be avoided because all the information goes to the other side of the event horizon, and also time asymmetry, because motion through event horizon is one-dimensional, so defines past and future. So you have time asymmetry at the event horizon, so the whole universe on the other side of the event horizon, I don't say inside, I say on the other side, could have the same asymmetry. So, and finally, just the last slide, torsion, I just only mentioned this, torsion could also explain matter-antimatter asymmetry in the early universe, because Dirac equation actually, if you make charge conjugation of Dirac equation in the presence of torsion, that the cubic term coming from torsion behaves differently for matter and antimatter. So this could potentially solve matter-antimatter asymmetry. And also in quantum field theory, torsion makes momentum non-commutative, which means instead of doing momentum integrals to calculate various things in quantum field theory, you have to replace them with summation over eigenvalues. And this is my newest research, basically 2 years ago. This may actually make renormalization finite, and we may have UV ultraviolet completion of quantum field theory. So torsion may actually solve many problems. So this is kind of nice research to do. So my acknowledgements for my URS University Research Scholar Program at University of New Haven, my students Gabriel Unger and Jordan Kubero, my colleague Dr. Shantanu Desai, with whom we make those nice pictures, and here my last slide, the summary of my main points. Thank you very much.
Thank you. Let's thank the speaker. And we already had a few questions during the talk, but I think we have a minute for one more or maybe two. So Antonina was first. Please, Antonina.
Hi, thank you. Thanks for this nice introduction. So I actually appreciate very much the framework. So I did appreciate as well also what you presented. I have a few comments. So one, what is the relation between the inflation that you considered here and the inflation scenario, let's say spin torsion motivated in Einstein-Cartan theory in the paper by Gasperini, PRL 1985. What is the relation of the math bounds scenario that you considered, and let's say the scenario with fermions, which basically is the same once you solve the Cartan structure equation, as proposed by Armendariz Picon and Patrick Green in a PhD, I guess, paper 2003. Also, I want to comment that the nice idea of indeed the fact that you can have a bouncing even effect a la Frolov inside black hole was actually studied by myself, by Leonardo Modesto and Cosmo Bambi in a paper PhD 2014. And finally, another comment / question, which is about the relation of the scenario that you're taking into account with respect to matter in a more particle physics sense, in the sense that, of course, we know that spin matter fields somehow has to condense or has to form a state of semi-classicality, more or less in the same way as it happens in condensed matter. Okay, so we know that matter exists and, of course, does not exist in clearly fermionic way, but in a state of semi-classicality that could be, for instance, a kind of a superconductive BCS state. So I was wondering if you have been also working on thinking in this direction, since, for instance, me and some other people, for instance, my collaborator Pisin Chen, Andrea Dazzi, Stefan Alexander, have been proposing several attempts to encoding indeed the fermionic condensation as a way to propose, for instance, from torsion, inflation, and even bounds with, for instance, Ifutsai and some other people. Thank you.
Thank you very much for great comments. Yes, so of course, what I was just showing here was like very simplified model. I used spin fluid approximation, and of course I mentioned that this is just an approximation. They're like a lot of research is doing, as you mentioned, right, about fermion fields could condense. This approximation I used may not be very accurate. I just used something which was done in the 70s and 80s, and I rewrote those equations in terms of temperature. I think this was maybe novel approach. Now for Gasparini model, yes, 1983 or 1, yes, about inflation, he used the same approximation. He used spin fluid. He had the same negative corrections to energy and pressure, and then I believe that I think the universe was flat in that model, but also I know that Gasparini found that in order to have inflation, then if the parameter which is in the equation of state between energy density and pressure is, I think, something about 1/3 or -1/3, but very close to the value, but not exactly, you can have period of exponential inflation. So basically Gasparini found a special case that torsion can make inflation for a very specific equation of state between energy density and pressure. Now here, my model would be different in the way that I assume that equation of state, so you have relativistic matter and you have basically extra corrections from spin, but my argument is that in my scenario, inflation would be caused by matter production at a bounce where quantum effects are very strong in strong gravitational fields. So that'll be the difference. Then also about universe in a black hole. Yes, of course, there's like a lot of articles, and you mentioned great articles about baby universes. So of course, here is, I think, the argument that I favor the scenario where it is torsion generated by spin within Einstein-Cartan theory, which provides.
This is exactly what was mentioned in this reference by me, Cosimo Bambi, Leonardo Modesto. I think I will email this to you. So
yes, thank you very much. I would love to, because I think I probably saw, but I want to, yes, definitely, because I would like to refer to see if there are probably big similarities. Hopefully, yeah. Thank you.